Welcome to the Deep Dive, the show where we grab a stack of fascinating sources and really distill them into the most important insights, helping you become truly well-informed. Today, we're diving into one of the biggest mysteries, I think, in the world of large language models. How can these incredible systems generalize new facts with, breathtaking speed, yet at the very same time be so notoriously prone to making things up, to hallucinating incorrect information?
Right. It's this a real paradox, isn't it?
Mhm.
A powerful superpower on one hand,
And a frustrating Achilles heel on the other. Exactly.
all rolled into one.
And our mission today is to unpack the underlying mechanisms behind this puzzling duality.
And what's truly groundbreaking, I think, about the research we're looking at today is that it doesn't just tell us that these behaviors occur. We kind of know that already. But it dives deep into the theoretical underpinnings, providing really innovative insights into why. We're going to get, quite academic in our explanation today, focusing on the fundamental findings that reveal the hidden biases, the sort of default pathways of how these models actually learn.
Looking under the hood.
Exactly.
Yeah.
At the core learning process itself.
That's right. So get ready to explore something called symbolic out-of-context reasoning, OCR for short in Transformers. Our mission today is to understand how a seemingly subtle architectural difference within these models can lead to really profound differences in their ability to reason, generalize, and sometimes conjure up pure fiction.
Okay, let's unpack this core concept first. Symbolic out-of-context reasoning, OCR. At its heart, it's about a model's ability to deduce new, unseen implications just by associating concepts it's learned, even when it hasn't seen the exact connection before.
Right. Think of it as true deductive learning, perhaps, not just pattern matching or memorization.
Yeah, exactly. And the researchers, they structure the information the models had to learn into what they call atomic knowledge. Imagine like a simple database entry for a fact. It's structured as a triple. You've got a subject, a relation, and an answer.
Okay.
So, for example, Louis lives in Paris. Louis is the subject, lives in the relation, and Paris is the answer, a basic unit.
Got it. Simple enough. And within this setup, they distinguish between two types of relations, right?
Correct. There's a fact relation, like lives in, and then there's an implication relation, like speaks.
Okay.
And the whole premise of this research, the setup, it hinges on an underlying rule they embedded into the data they created. This rule basically says, if a subject has a fact relation with a specific thing, let's say, a city, it implies they also have an implicate relation with a corresponding other thing, like a language.
So sticking with the example, Louis lives in Paris implies Louis speaks French.
Precisely. It's a crucial one-to-one correspondence.
Yeah.
One fact answer, city, maps directly to one implication answer, language.
And this setup, it allowed for a really innovative way to test if a model is actually reasoning out of context. Yeah. Not just remembering stuff.
Exactly. And here's how they constructed the data set, because this is really key. They first partitioned all the subjects into separate groups. Then they split these subjects into training and test sets.
So if we take our example, they might have a group of city language pairs, like Paris, French, Rome, Italian, Berlin, German, and they create subjects for each city.
Yeah, something like that. Now, for the training data, they included facts for all subjects. So whether Louis was in the training group or the test group, the model would see Louis lives in Paris. It gets that fact.
Okay.
But crucially, they included implications only for the training subjects. So the model would only see Louis speaks French if Louis was designated as a training subject.
And the test data then, what was in that?
The test data, well, it consisted solely of implications for the test subjects.
Only implications.
Only implications, and only for those subjects the model hadn't seen implications for during training. This is the ingenious part. So, for a test subject, let's call her Marie, the model would only have seen Marie lives in Berlin. That's the fact.
Yeah.
It would not have seen Marie speaks German during training.
Right, so it has to figure that out.
It forces the model to predict the implication for Marie based only on the underlying rule it had to learn from the training subjects. It can't just remember a specific Marie-German pair because it never saw one.
Wow. That's a really rigorous way to ensure you're measuring actual generalization. Out of context reasoning, truly.
Exactly. Isolating that ability.
And the experiments on popular LLMs, you mentioned Llama 3, Mistral 7B, they delivered quite the stark result, didn't they? Confirming this double-edged sword idea.
They really did. When the fact and implication were causally related, like our city language example where Paris naturally implies French, these models showed strong generalization They performed exceptionally well. They learned the rule.
Okay, so far so good. That's what we want them to do.
But here's the twist. When they used counterfactual or non-causal links, for instance, a city language counterfactual dataset where, say, Paris implies Japanese.
Which makes no sense causally.
Right. Or a completely arbitrary profession color link. In those cases, the exact same associative ability that drove the good generalization before. It led to significant hallucination. The models would confidently predict these incorrect associations because they were just applying that learned association mechanism, like indiscriminately, even when there was no logical basis for it.
So the mechanism itself isn't inherently flawed. It's just applying a pattern-finding tool where there's no meaningful pattern.
You could put it that way. It clearly demonstrates the duality. The very strength that lets them generalize also makes them invent things when the underlying logic is broken or just absent.
Fascinating. So this duality in the empirical results, that set the stage for the really deep theoretical dive in this paper, right? To figure out the why. Okay, so we've seen that this duality exists in real LLMs. But the truly fascinating question, the one that gets researchers really digging, is why? What tiny hidden difference causes such a huge split in abilities? Generalization versus hallucination.
Precisely. And to get at this why, the researchers turned to a simplified model. A one-layer, attention-only transformer.
Not a massive LLM like the ones they tested initially.
No. Much simpler. Think of it as a controlled sandbox. It lets you understand the fundamental learning mechanisms without the, overwhelming complexity of billions of parameters and multiple layers.
Makes sense. Keep it simple to find the core principle.
Exactly. And here's where it gets really innovative and central to their contribution. They compared two seemingly similar versions of this simple transformer. They call them the factorized model and the non-factorized model.
Factorized and non-factorized. Yeah. Okay.
Now, on the surface, both models have identical expressive power, which means, theoretically, they could learn the same things. They could both achieve perfect performance on the task.
So, mathematically, they look like they should be able to do the same job?
Pretty much, yeah. But their internal parameterization, how they're built inside, specifically how they structure and combine certain internal weight matrices, particularly the output matrix, WO, and the value matrix, WV.
Yeah.
That makes all the difference, not in what they can represent, but in how they learn.
It's like they have the same number of bricks, but how they're snapped together inside is different.
That's a great analogy, yes.
Yeah.
And that difference in internal structure dramatically changes their learning dynamics.
Okay, can you give us a bit more detail on that difference? Factorized versus non-factorized.
Sure. So the factorized model, it reparameterizes the combined output value matrix, let's just call it WOV for simplicity, as WO times the transpose of WV. Oh, wait, sorry. It's WO times the transpose of WO times WV.
Okay, technical detail, but the point is it breaks it down.
Yes, it forces a specific structure, WOV, WOVAVT. This structure, this factorization, guides the model to learn in a more structured way. Think of it like a chef learning individual components, the output flavor, the value texture, and then figuring out how to combine them flexibly. This structure is what helps it learn the key for OCR.
Okay, so that's the factorized one. What about the non-factorized?
The non-factorized model just lumps it all together. It directly learns a single combined WOV matrix. There's no breakdown, no forced structure like in the factorized version.
So back to the chef analogy.
Yeah, it's like the chef who only learns whole pre-made dishes. They can replicate those dishes perfectly, maybe.
Yeah.
But they struggle to create something new because they haven't learned the underlying components separately. It just learns the combined effect directly.
And the empirical results from comparing these two simple models, was it as stark as with the big LLMs?
Oh, absolutely stark. The factorized model. It achieved zero test loss on the unseen data. Perfect generalization. It learned the rule beautifully. The non-factorized model. Complete failure to generalize. It was basically making random guesses on the unseen implications. Zero accuracy above chance.
That's incredible. So a seemingly small architectural choice, just how you structure the math inside.
Even if they're theoretically equivalent in what they could express.
Right. That choice dictates whether it's a brilliant generalizer or just a memorizer.
Exactly. And this architectural insight, showing how parameterization impacts learning dynamics despite equal expressive power, that's a major innovation point in this research. It really highlights that the learning process, the path the model takes during training, matters profoundly.
Okay, this brings us to the really core theoretical innovations of this paper. Because just showing the difference isn't enough. They explained why it happens. They analyzed something called the implicit bias of gradient descent. Now that sounds dense. What exactly is implicit bias in this context?
Yeah, it's a key concept and central to this work. Think of implicit bias as the hidden preferences,
Hmm.
or maybe the unconscious shortcuts that a learning algorithm like gradient descent takes when it's trying to find a solution.
So even if there are many ways to solve the puzzle, the algorithm kind of prefers certain types of solutions.
Precisely. Even if multiple sets of internal weights could perfectly explain the training data, the way the model learns its training dynamics, how gradient descent updates the weights will implicitly push it towards one kind of solution over others.
It's like you could walk or bike to the same place, but the act of biking inherently favors smoother paths.
That's a really good way to think about it, yes. The learning algorithm has its own preferred terrain.
So what hidden preferences did they uncover for these two models, the factorized and non-factorized?
Okay, so for the factorized model, the one that generalized well, its training process implicitly biases it towards minimizing something called the nuclear norm of that combined WOV matrix.
Nuclear norm. Okay,
Yeah.
what does that mean intuitively?
Intuitively, minimizing the nuclear norm encourages solutions that are low rank. Think of low rank as meaning simple, structured, capturing the main patterns without unnecessary complexity. It pushes the model to find the most compact, elegant explanation.
Like finding one master key that opens many doors instead of a giant key ring.
Exactly. It implicitly pushes the model to find that underlying linear rule, the one-to-one mapping between facts and implications. This low-rank structure is the generalization mechanism here. It's a mathematical proxy for finding the underlying rule.
Fascinating. And the non-factorized model, the one that just memorized and failed the test, what was its implicit bias?
For the non-factorized model, its implicit bias pushes it to minimize the Frobenius norm.
Different norm, different preference.
Right. And the Frobenius norm doesn't particularly encourage low-rank solutions. It's more concerned with making the magnitude of all the individual weights small. It often leads to dense, unstructured weight matrices. It's like trying to fit every single data point perfectly, even if that means creating a really complex, wiggly line instead of a simple straight one.
So no push towards that elegant, simple rule.
Exactly. Without that structural encouragement from the nuclear norm bias, the model defaults to just memorizing the training examples it saw. It never grasps the general principle, which is why it fails completely on unseen test data.
Okay, but here's where it gets really interesting, I thought. They didn't just say it fails, they dug into why the non-factorized model fails so spectacularly. It involves parameter symmetry and permutation equivariance. These sound super technical.
They are quite technical, but the core idea is actually pretty elegant and provides a deep explanation. So remember how the data set had this uniform structure? Any subject-fact implication set was basically interchangeable with another from the model's learning perspective.
Yeah, Paris French is structurally the same as Berlin German in the setup.
Right. Because of this uniformity, the non-factorized model's WOV matrix inherently tends towards a symmetric state during training. But the researchers proved something even stronger. They showed that the gradient field of the loss function, basically the landscape the model navigates during learning, is permutation equivariant.
Okay, permutation equivariant. Break that down. What does that mean for how the model learns?
It means that if you swap around the labels for the different implication answers, like swapping French and German, the direction the model wants to adjust its weights to reduce error also swaps around in the exact same way. The learning process itself respects the symmetry of the problem.
So the model's adjustments are fundamentally tied to the arbitrary way the answers are presented. It can't break free from that symmetry.
Precisely. That property, combined with another technical condition called Lipschitz continuity, which just ensures smooth learning guarantees that the learned weights, WOV, will also maintain this symmetry throughout training. And here's the killer consequence. This symmetry means that for any test subject, where it only saw the fact, not the implication, the model's final WOV matrix assigns equal probability to all possible implication answers.
It literally cannot distinguish between French, German, Italian.
Exactly. It learns that some implication exists, but because of the inherent symmetry enforced by the learning dynamics on this architecture, it cannot learn which specific implication corresponds to which fact for the unseen subjects.
Its hands are tied by its own structure and the learning process. Wow.
It's forced to guess randomly because its internal representation for those unseen implications is completely symmetrical, totally indistinguishable.
That theoretical explanation, with the proofs and even the closed-form solutions they derive for the weights, That feels like a major piece of the puzzle, a really deep academic insight into why this specific architecture fails.
Absolutely. It's a rigorous explanation of the failure mode, rooted in the fundamental mathematics of the learning dynamics.
So let's pull this all together. What does this mean for you, the listener, trying to understand these complex AI models, and what are the bigger implications for the field?
Well, I think this research provides a really solid theoretical foundation for understanding the double-edged sword we started with.
The generalization versus hallucination?
Yes. The underlying mechanism that allows for powerful generalization, that ability to associate concepts efficiently, which seems driven by this implicit bias towards low-rank structures, minimizing that nuclear norm. That same mechanism makes LLMs vulnerable to hallucination when the associations aren't, causally grounded or factually correct.
Because it's always trying to find some simple structure or association.
It seems so. Its drive to find structure, learned through this bias, means it might impose one even when it's not really justified by the data or reality. It's applying its powerful pattern-finding tool indiscriminately.
And it's incredibly sample efficient, you mentioned. That seems key, too.
Hugely important. The paper points out these models can learn these associations from very, very few examples, sometimes just a handful of training subjects in their experiments.
That explains the power of few-shot or in-context learning we see in big models.
Exactly. It's incredibly powerful for rapid knowledge acquisition. But it also helps explain why new information, even if it's spurious or incorrect, can quickly lead to widespread and confident-sounding hallucinations if the model latches on to a faulty association.
A little bit of bad data can go a long way in the wrong direction.
Potentially, yes, if it creates a strong, simple, but wrong association. And there's another significant implication, more for the researchers building and studying these models.
Okay.
Many theoretical studies use these kinds of reparameterizations, like the one defining the non-factorized model, because they often make the math simpler or computations easier.
Right, simplifying assumptions.
But this study is a stark warning. It highlights that such reparameterizations, even if they seem equivalent on paper in terms of what the model could represent, can profoundly alter the training dynamics. The implicit biases change.
And therefore, the actual learning outcomes change, especially generalization.
Precisely. It's a critical academic contribution, really calling for careful thought about whether a chosen simplification is actually appropriate for studying the phenomenon you care about, like generalization. The how of training matters just as much as the what of the architecture.
It truly is a deep dive into the underlying intelligence, or maybe the specific kind of intelligence, and its limitations in these transformers, explaining not just what they do, but offering a mathematical why.
And that kind of rigor is absolutely essential if we want to build more robust, reliable, and truly trustworthy AI systems down the line.
And that's our deep dive into symbolic out-of-context reasoning. We've seen how subtle architectural differences like factorization can have these profound impacts.
Yeah, how hidden mathematical biases, these implicit preferences like minimizing nuclear norm versus Frobenius norm, really influence what gets learned.
And why that line between brilliant generalization and, let's face it, frustrating hallucination is just so thin for LLMs. It's almost two sides of the same coin.
It really seems that way based on this analysis. This deep dive has shown how getting into the fundamental theory, the nuts and bolts of implicit bias and matrix norms, can really illuminate these complex practical behaviors we see every day.
Yeah, it underscores the importance of looking under the hood, understanding those core mechanisms. So what stands out to you, listening to this, perhaps it's that core idea. And a model's generalization superpower is also its hallucination Achilles heel. Next time you see an LM doing something surprisingly smart or maybe surprisingly wrong, perhaps you'll have a deeper, more academic sense of the mechanisms potentially at play. And maybe this makes you wonder if these simplified one-layer models reveal such profound biases and dynamics, what hidden complexities, what other implicit assumptions might be shaping the behavior of the vast multi-layered transformers we interact with every single day. Something to think about. Thanks for diving deep with us. We'll be back soon with another stack of insights.